Bismillahirrahmanirrahim. Dear students, today we are going to discuss about Hofmann-Leffler-Freytag HLF reaction. This reaction is basically about the carbon-nitrogen bond formation, and also this bond is in the cyclic form. That is, this new carbon-nitrogen bond is formed in a cyclic manner. You can say this 5-membered in the form of a 5-membered cyclic ring, which is also known as pyrrolidine. So Hofmann-Leffler-Freytag reaction is basically about the synthesis of pyrrolidines or the derivatives of pyrrolidines. The key points of today's lecture is slight introduction about the HLF reaction, which we have also discussed in the previous lecture. The overall mechanism of HLF reaction, and then we shall move towards the modification made in HLF reaction, the mechanistic studies of HLF reaction by Coro. This mechanistic study basically includes the different factors or clearance or explanation for the different factors, including stereochemistry or abstraction of proton or initiation, inhibition of the reaction, catalysis of the reaction, and in the end we shall discuss about the synthetic applications of this HLF reaction on various substrates. Hofmann-Leffler-Freytag reaction was first time given by A.W. Hofmann in 1878, about 1 century, more than 1 century, 150 years ago. And after that, in 1909, K. Leffler and C. Freytag worked on the reaction mechanism of this Hofmann reaction. Basically, this method is about the synthesis of pyrrolidines. This pyrrolidine uses the substrates of N-halogenated amines. These N-halogenated amines are converted into cyclic heterocyclic amine through an intramolecular 1,5 hydrogen atom transfer or hydrogen atom shifting to a nitrogen radical. So the conversion of this N-halogenated amines into pyrrolidines is achieved through the acidic conditions, followed by applying heat, thermal energy or the sunlight in the form of visible light or UV light, and finally the product is achieved by the workup through the use of base. Here you can see the general reaction in which an N-halogenated amine is converted into pyrrolidine. First step is the use of acid along with heat or sunlight, and second step is the use of base to finalize the product. In general form, it can be written is also that N-halogenated amine in which R1 can be alkyl, aryl or hydrogen, and R2 can be alkyl, acyl or hydrogen, and X can be chloro, bromo or hydro, are treated in the presence of sunlight, heat or some radical initiator to get the delta halogenated amine. That is, this is an intermediate which is formed after 2 or 3 steps, and by the use of base we get the cyclic amine, which is also known as pyrrolidine. The conditions can be acidic or neutral or weakly basic medium, and we get the product of this pyrrolidine. These the conditions vary with the variation in the nature of the substrate. Here you can see the this reaction forms only 5-membered ring, and mostly or predominantly most of the time this 5-membered ring is achieved, is synthesized instead of some other ring. That is, the abstraction of proton is from the delta carbon, which is at the 4th position from the nitrogen, and we get the finally product. We shall discuss about the reason of this abstraction from this position on next slides. Here is the overall mechanism of this HLF reaction. The first step is the protonation of this chlorinated amine. Here is it can be any haloamine, but here is the case, in this case is chloroamine, which is protonated by an acid like sulfuric acid, generally used in high concentration, and we get the ammonium ion. In the next step, this ammonium ion is homolytically cleaved into chlorine free radical and nitrogen free radical. This nitrogen free radical with positive charge is also named as ammonium ion. This ammonium ion can be represented in a cyclic manner. As you can see here, this is showing a 6-membered ring. Through this 6-membered ring, transition state of this 6-membered ring, this reaction, this species goes into 1,5 hydrogen atom abstraction, and we get the radical on carbon instead of nitrogen. Here you can see the way of mechanism, that one electron from nitrogen is moving toward the hydrogen, and the carbon-hydrogen bond is broken in such a way that hydrogen comes with its electron towards nitrogen, and we get the formation of NH bond, and simultaneously the CH bond is broken, and we get the carbon with a free radical on it. This mechanism is also thought to be a move in a concerted manner. Here you can see this will surely move in concerted way. At the same time the bond will be formed, and the same time the old bond will be broken. In the next step, this carbon free radical is treated with the first protonated chlorinated amine, that we termed as ammonium, before the step of homolytic cleavage. So this chlorinated ammonium is now acting as a chlorinating agent, and it will provide chloride in the form of chlorine radical. This chlorine radical will attach with this carbon radical, and we get an alkyl halide. At the same time we will get the free radical on nitrogen with positive, that is ammonium ion, ammonium radical. In this way, this sort of a propagation moves on, and we get a radical chain from this reaction. We also term this step as propagation. The first step was the initiation, in which free radicals were produced through homolytic cleavage, and this step is the propagation of free radicals, in which chains is moving in the form of free radical. One free radical is finished, and at the same time another free radical is created. In the next step, this ammonium alkyl halide containing ammonium species is treated with the base. The base abstracts a proton from nitrogen, this ammonium ion, and we get the lone pair of nitrogen free. This lone pair, acting as a nucleophile, attacks on the carbon bearing the halo group in a SN2 reaction mechanism, and the chlorine is abstracted in as a chloride ion. Cl minus ion is separated, and we get the cyclized ring, in which nitrogen is with positive charge because of formation of 4 bonds. In the next step, again other molecule of base comes and abstracts another proton of nitrogen, and we will get the neutral pyrrolidine structure. during at the time of workup, this species worked up in acidic medium because no, sorry, there should be basic medium, because if we apply the acidic medium, then this nitrogen will protonated again, and this positive cation will be solubilized by the medium, and we will not be able to get the product. So this product should be obtained in a slight acidic medium, slight basic medium instead of acidic medium. Here are given some modifications in this HLF reaction. The modification, because we were using strong acidic conditions for the basic HLF reaction, and these strong conditions may be not compatible with sensitive functional groups or protecting groups of complex substrates. So therefore there were made some modifications in the nature of the substrate, in the reaction conditions, in the workup manner, so that we can get the product from a different number of molecules, or avoid certain complexities which are side reactions which were faced in the basic HLF reaction. So first modification was the photolysis of N-haloamides, that is, instead of N-haloamines, N-haloamides were used as the substrates, and these proceed through the neutral conditions instead of original acidic conditions which were used for the N-haloamines. Here you can see the reaction. First reaction is the cleavage of this bond in sunlight, and here you can see there is no protonation is done, and we get the product here in which N-halo bond is cleaved in the presence of sunlight, and we get the N radical which is further moved after cyclization into this new cyclized ring. Here you can see in this first step that the N-bromoamide was converted into amine and alkyl halide, which we know is obtained after 2 to 3 steps of reaction mechanism, and then finally we get the cyclized product, but this cyclized product with the oxygen instead of nitrogen. This thing, first thing which should be explained here, why proton is not involved in this reaction, there is no need of protonation. Why? Because the protonation was only to capture the lone pair of nitrogen so that it may not interact or disturb during the reaction mechanism. But here you can see when the nitrogen is present in the vicinity of a carbonyl, then the lone pair of nitrogen is resonating towards the carbonyl, and so there is no need to capturing this proton by acidification or protonation, or we can get simply the product. But this product is with oxygen cyclized, because the lone pair of nitrogen was resonating towards the carbon, and oxygen was getting the O minus charge. This negative charge was more nucleophilic, and that attacks on the carbon of bearing halo group, and we get the cyclized product, but this cyclization is with oxygen, not that of nitrogen in this case. But this case is not always the same. Here you can see another second example in which acetamide and chloroacetamide is treated in the presence of sunlight. We get 43% yield, and we get the product of this N cyclization. You can see here this cyclization is through nitrogen, and after a large number of steps we get the finally product which is a synthetic drug. The second modification was the use of sulfonamides as a starting material instead of N-haloamines or simply amides, And these sulfonamides are known to undergo gamma or delta halogenation under neutral conditions by using or in the presence of persulfates. These persulfates can be peroxysulfate SO5 2 minus or peroxo disulfate S2O8 minus 2, in also with the presence of some metal salts. Here you can see the example in which a sulfonamide is treated with sodium peroxo disulfate and cuprous chloride, cupric chloride CuCl2 is used along with it, and we get the product in which there is both products are obtained. One is with gamma halogenation and one is with delta halogenation. Gamma halogenation is giving only 10% product, but the gamma halogenation is giving 65% yield. Second different category or modification of this HLF reaction was studied by Kimura and Ben. Both of these scientists used N-chlorinated or N-haloamine, but it was a cyclized amine, and in its neighboring position or a delta position there was present another nitrogen, also a heterocyclic ring nitrogen. So it was observed that this nitrogen which is present at the alpha delta position of this N-haloamine was involved in the stabilization of the free radical, and so there was the fast reaction as compared to the other reactions. So they concluded that the adjacent nitrogen atoms can stabilize alkyl halide species and so require weak basic conditions instead of strong acidic conditions which were used in the basic HLF reaction. And better yields were obtained in photoirradiation in the presence of triethylamine used as a base. This base also involved in the neutralization of HCl which is produced during the reaction. Here you can see the two examples. First example in which nitrogen chlorine bond is broken and we get free radical on nitrogen, then it abstracts proton from the carbon which is present and at the adjacent of the second nitrogen, and then this free radical after halogenated converts into free radical alkyl halide, and then we get the final product of the cyclization of the ring. This cyclization is about 6-membered ring is produced here. In the second reaction you can see the similar type of example in which more cyclic rings are present in the substrate, and we get the similar type of results, and we get the product here. One thing can be explained here about the stereochemistry. Here you can see the nitrogen chlorine bond is broken and we get the nitrogen free radical. Okay, this free radical abstract proton from this the carbon in the vicinal of other nitrogen, and this carbon gets the free radical. As you know, the free radical has sp2 hybridized structure, not sp3 hybridized structure. So as we know, sp2 hybridized free radical is a planar structure, and in case of planar structure there will be chances for the attack of the lone pair of nitrogen, attack of the chloride free radical from upper side or below side. So there will be the formation of halo group, there are chances of both sides, and then when the lone pair of nitrogen attacks on this carbon, it will always attack from the opposite side of the halo group, that is SN2 reaction mechanism, and we get the stereochemistry of the product according to this type of attacks or this way of attack. Here you can see the stereochemistry of the last amine hydrogen is moving, is shown by the dotted, and the bond formed with the carbon and nitrogen is shown in the thick line, that is planar. The most important modification made in HLF reaction is the Suarez modification, and which has been used by the different scientists in a number of ways. First thing difference in this modification is it uses the substrates which are N-nitroamides or N-cyanamides or N-phosphoroamidates, or you can say N-phosphoramidates. Here you can see the structure of these substrates also at the end, where the general structure is shown in which nitrogen is attached with an electron withdrawing group EWG, and this electron withdrawing group can be NO2, CN or phosphonate. Here you can, if it is NO2 then it is termed as N-nitroamide, if this is CN then it is named as N-cyanamide, and if it is phosphonate then it is N-phosphoramidate. All of these react with the hypervalent iodine reagent. Hypervalent iodine reagent, because you can see in the reaction there is written LTA or PIDA. LTA is lipotecoic acid, which is giving acidic conditions, or the second is option is PIDA. PIDA is phenyl iodine 3-diacetate. Here iodine is in a hypervalent state because it is making will be making 3 bonds in its structure. We will show this structure in the next slide. So these hypervalent iodine reagent are that LTA converts in the presence of iodine, converts this NH bond, activating in the form of alkylate. So there is no need of homolytic alkylation here at this step, and we get the formation of iodoamide intermediate in which nitrogen is bearing iodine. First step is a difference from the last basic mechanism. The second step and the third step, next steps are the similar as we have described for the basic HLF reaction, and we get the final product in which pyrrolidine ring is created. Other feature of this reaction is that the conversion of this iodoamide intermediate is under neutral conditions to generate nitrogen centered radicals via the hypothetical iodoamide intermediate. That is, we convert this iodoamide intermediate into nitrogen centered radical, but this is under neutral conditions. There is no need of protonation of this nitrogen. Due to presence of these strong electron withdrawing groups, there will be no need of protonation, as we have discussed in the case of amide also. There was no need of protonation. The notable feature of this method is number 1, generation of unstable iodoamide intermediate. Unstable iodoamide intermediate mean there will be the fast conversion of this intermediate into the product side. Second, the iodoamide homolysis proceeds thermally at low temperature, about 20 to 40 degrees C, which is too much lower as compared to the normal HLF reaction. Also by irradiation, but irradiation is also through simple visible light instead of UV light, which has been used for the basic HLF reaction. So we get the final product of pyrrolidine here. Here was the another mechanistic study by the E.J. Corey. This study involves the discussion of different factors, that is stereochemistry of the mechanism of the product, the abstraction of proton, nature of abstraction, or you can see the inhibition, propagation, or catalysis of the reaction. Here we discuss first the stereochemistry of this HLF reaction. If you see, in order to determine whether the replacement of hydrogen in the cyclization of N-haloamines proceeds with retention or inversion or equilibration of configuration, deuterated amine was synthesized and that was proceeded to the reaction. Here you can see the reaction also. The deuterated amine was chlorinated, followed by thermal decomposition of the resulting N-chloro derivative in the presence of sulfuric acid at 90 degrees C, and we get the optically inactive 1,2-dimethyl pyrrolidine. Optically inactive means there was the formation of a mesocomplex. This experimental observation was a strong evidence in favor of the intermediacy of a species with an sp2 hybridized gamma carbon. As we have discussed in the last slide, that the free radical produced at the carbon is sp2 hybridized, and when the chlorine free radical attacks on that free radical to form alkyl halide during the reaction mechanism, then there are chances for the attack from both sides. So there are the chances for the formation of both types of optically active compounds and resulting into an optically inactive species. The second discussion was about the initiation of reaction. An example of N-chloro di-N-butylamine was taken, and it was found that it was stable in 85% H2SO4 at 25 degrees C at room temperature in the dark, but it began to disappear soon after irradiation with UV light. That is, the initiation is the required step for the reaction proceed of the reaction. It will not proceed itself. And also the incubation period of the reaction is about 12 minutes after the start of irradiation. That is, irradiation is necessary for the initiation of the reaction. Second was the inhibition of the reaction. Inhibition of the reaction was found by the molecular oxygen, because when the reaction was proceeded in nitrogen atmosphere, that is oxygen free atmosphere, free condition, it was too much fast as compared to that which was in the presence of normal air. So it was concluded that the molecular oxygen has been involved in the inhibition of reaction, and if we free the atmosphere from this molecular oxygen, we can speed up the reaction. Third point is the catalysis of the reaction. The catalysis reaction in the dark by the addition of catalytic amounts of ferrous salts to a solution of dibutyl chloramine in H2SO4. That is, N-chloramine in H2SO4 is already present, but if we add ferrous salt as a catalyst in catalytic amount, although it is present in dark, the reaction will be started. That is, initiation is given by this ferrous ion through an oxidation reduction process. Second, the rate of the UV catalyzed decomposition and yield are strongly dependent on the acidity of the reaction medium. That is, fast reaction and high yield has been obtained with the increased sulfuric acid concentration, but too much high concentrations also have some negativity or negative effect, but in general high concentration of sulfuric acids are recommended for the proper movement of the reaction. Here is the third category, that is selectivity of hydrogen transfer. Which hydrogen will be abstracted by the nitrogen free radical to result into the product side. First thing is that with the abstraction of proton by the nitrogen free radical, we will get carbon free radical. That can be primary, that can be secondary, that can be tertiary. So there is given preference with the stable free radical. That is, tertiary free radical is give preference over secondary, and which is given preference over primary. Here you can see the first example in which you can see nitrogen is tied with two alkyl group. One side is with N-butyl and other side is with N-pentyl, but the cyclization occurs through N-pentyl, not through N-butyl, because the free radical, the free radical will be produced at the delta position, that the fourth position from the nitrogen. The fourth position from the nitrogen of butyl group is primary carbon, that is, primary free radical will be produced, but the fourth position in case of N-pentyl there is secondary carbon, and so secondary free radical will be produced, which is more stable. So cyclization occur through this N-pentyl side, and we get the cyclized product. At the other, the cyclization through N-butyl is not detected, that is even 0% detection. Similarly, strong preference is given for tertiary over primary and secondary hydrogens. Here you can see the example, one side is with N-butyl and other side with iso cyclohexyl. If you see the N-butyl, then we will get the free radical of with primary carbon, which is given not given preference, but we get the free radical in which carbon of tertiary carbon is getting the free radical. Second thing which can you see here, that this tertiary carbon of isocyclohexane or hexyl group is converted into free radical, and it is converted into protonated form, and ammonium we get it in the halogenated form also. But after that step, this is readily solubilized by the medium, and we do not get the pyrrolidine structure by pyrrolidine product. So therefore it is concluded that tertiary was given preference over primary and secondary, but the tertiary form was not able to be converted into product due to solubilization problem. Next is the relative ease of 1,5 and 1,6 hydrogen migration. Shows a 9-1 mixture of 1-methyl 2-ethyl pyrrolidine and 1,2-dimethyl piperidine. Here is the mixture is shown here, and you can see the substrate here. That is the chances of 6-membered are there, and chances of 5-membered are there, but 5-membered has been given preference. The reason of this thing can be explained through the stable 6-membered transition state, which follows the chair form of the cyclohexane species and moves into the product site. Last thing, too much slow reaction have been observed for the methyl cyclohexyl chloramine, which you have seen here, first molecule, and second is the N-chloroaza cycloheptane, cycloheptane having nitrogen heterocyclic ring, and then as compared to that of N-butyl chloramine, because in case of N-butyl there are sp3 hybridized carbon, hybridized carbon with single bond, and also there is chances of sterically approach towards the nitrogen free radical, and so we get the product for easy product for the dibutyl chloramine, as compared to the other two which contain cyclic rings. And as you know, there will be much steric hindrance for the formation of cyclic ring from the nitrogen free radical towards the gamma delta carbon of the cyclic ring. So there are less chances for the ring formation toward the cyclic static, or you can say solid rings. So there are the reaction for these substrates is very slow. Here are some synthetic applications of this HLF reaction. First we discuss the standard conditions. The standard condition means the strong HD conditions and thermal or sun ultraviolet radiations, and also in the last step the use of base for the workup. Here you can see the first example in which N-chloroamine bearing an ester moiety also is treated in the basic condition, and we will get the 5-membered ring here in a very good yield of 85%. Second, in which we are using piperidine ring, that is nitrogen is present on the ring, but it has cyclic aliphatic chain also at the vicinal position. So after applying the basic conditions we get the cyclized ring, but it is only 25% yield of the reaction, and there is a mixture of the in case of stereochemistry there is a mixture, formation of mixture, because you can see alpha and delta carbon, there is up to the formation of 5-membered ring. Second, next is the also formation of ring with N-chloro secondary amine, which is treated in organic trifluoroacetic acid, that organic acid, and we get the cyclized ring with 26% yield only. The last example here is the bicyclic amine is treated. Bicyclic amine, that is, there is already steric observation. In the presence of N-chlorosuccinimide, it is first, this amine is first chlorinated by N-chlorosuccinimide in dichloromethane at 0 degree C with 85% yield, and this resulting bicyclic N-chloramine is treated with the trifluoroacetic acid at room temperature and then with the base under reflux, and we get the product with only 38.7% yield, and the resulting product is shown here also. Here are some other examples under standard conditions in which N-chlorosecondary amine is converted into the product with only 34% yield, and next is N-bromosecondary amine, which is converted into the product with 25% yield, and the third is also N-chlorosecondary amine, which is converted into the cyclic product with only 10% yield. Here you can see that in all of these cases you are observing in the normal or basic standard conditions which were used by basic HLF reaction are resulting into the yield, but the yield in too much low form, that is the percentage yield is too much low, which is not synthetically preferable. Here are some different cases with the synthetic application under standard conditions. Here you can see the natural products which have been converted into cyclic rings after chlorination of them, that N-chlorosecondary amines have been used, but we get the product with first reaction with 85% yield, second with 90%, third is the 72% yield. That is, in case of these rings there is the formation of 5-membered ring, and that is also in a very good yield, high percentage yield, as compared to that one which were for the simple aliphatic chains or simple monoamines or monocyclic rings. So multicyclic amines and chloramines bearing multicyclic rings have given too much better yield. Now we discuss some modification reactions of the basic HLF reaction. First, here the starting substrate is the sulfonamide, and under mild conditions we get the product, cyclized product. Here you can see the first step is the iodine N-halo formation on the sulfonamide moiety, and then after free radical H5 shifting and movement through the other reaction intermediates, we finally get the cyclized ring with 2 halo groups, and that is hydrolyzed, and we get the ketonic carbonyl group at nitrogen in the vicinity of the nitrogen, which is the cyclized product of nitrogen finally. Next is also the use of a sulfonamide. In first step is the iodination and heating, and then we get finally the cyclized 6-membered ring is also produced here in this case. Basically it is a formation of CH bond, a CN bond, carbon and nitrogen bond, and we get the 72% yield. But here we get the 6-membered ring instead of 5-membered ring. First example is also sulfonamide, which has been converted into the cyclic 6-membered ring after iodination, and we get here X can be hydrogen. If X is hydrogen, then we get 6% yield, and if X is iodine, then we get 89% yield. That halo groups are activating this molecular species for the formation of this cyclic heterocyclic ring. Next is example of a cyclic amide, which is after iodination converted into 5-membered ring, very easy manner, and also very good yield of 82%. Next example is the use of simple amine, you can say secondary amine, which is treated in the presence of PIDA with iodine, and then after workup we get the final cyclized product of 5-membered ring. And second example, which is taking the substrate with bearing the phosphonate group, and so we have phosphor amidate moiety here as a substrate, which is converted into iodination first and then move through the other reaction steps, and we get finally the product of 5-membered ring. Here are the structures of these used species. That first is the PIDA, PIDA. We have this also mentioned in the last slide, that phenyl iodine 3-diacetate, PIDA. Here is the structure where as you can see the iodine with trivalent state, that it is directly attached with one phenyl ring and 2 with the 2 oxygen or 2 acetate group. And second, in the last reaction you see the PHIO. The structure of this is iodosobenzene or iodosyl benzene, pH for phenyl, iodine and oxygen, or you can say 6 is H5IO. The structure of this species also here, the iodine also making 3 bonds, that is hypervalent state. Here is the last 3 examples under which have been performed under mild conditions, that is the amine bearing some electron withdrawing group. And here you can basically this is about the Soares modification reaction, which we have discussed in the last slides. So this the percent yields have been given here for all of these species. If for the first reaction, if X is nitro, then we get 63%. If X is cyano, then 64%. If X is phosphonate, then we get 99% yield of the product, cyclized product. Similarly, in the second case, if the X is the nitro, then we get X nitro and R is the CH3, then we get 43%. If X is nitro and R ester moiety, then 65%, and if X is phosphonate and R is the an ester moiety also, then we get the 90% yield. In the last reaction there is amide which has been used, and we get the cyclized product through nitrogen, and we get it with 80% yield. So there are 2 types of synthetic applications have been discussed here. First under the basic conditions, and second under the mild conditions or modified conditions. So this was all about of the HLF reaction, and thanks.